Hello everyone, I am Ms. Disha Purohit and I would be presenting the paper titled Towards Interpretable Hybrid AI, Integrating Knowledge Graphs and Symbolic Reasoning in Medicine on behalf of all my co-authors. In lung cancer, diagnosis and treatment decisions are intricate, while oncologists needing to consider numerous factors including tumor type, stage and genomic markers to develop patient-specific treatment plans. These factors guide crucial decisions regarding therapies, dosages, and treatment cycles tailored to individual patient responses and comorbidities. The primary clinical objectives in lung cancer management include maximizing the survival time and quality of life of the patient, minimizing side effects, and preventing relapse and disease progression. Although oncologists rely on their expertise and established guidelines, the variations in patient cases often makes it challenging to determine optimal treatment strategies through intuitive means alone. Predictive models could assist in diagnosis, treatment planning, and relapse prevention. However, traditional models frequently lack interpretability and domain specific insights, crucial in lung cancer management, where precision and transparency are essential. To, to address these challenges, leveraging medical semantics can significantly enhance both the accuracy and interpretability of predictive models. Hybrid AI integrating symbolic reasoning with inductive learning over knowledge graphs present a promising approach to overcome these challenges. This approach combines interpretability and adaptability, thereby offering clinicians a deeper, more tailored understanding of a specific patient need. Semantic data management helps to combine different types of data, including scientific literature, clinical guidelines, and patient records. This layer makes the data from different sources align with each other, creating a unified and interoperable schema that captures complex biomedical knowledge within an integrated data system. This structured approach allows data sources to be mapped to unified schemas or biomedical ontologies, example the Unified Medical Language System. Clinical protocols and guidelines are encoded as shape constraints. Domain-specific representations are used to make outputs produced by TrustKG easy to understand and relevant to the context. Knowledge graph management helps to create, validate, and explore knowledge graphs. It uses shape schemas to validate the graph, ensuring it is consistent and reliable. Federated query processing allows seamless exploration and across multiple datasets. Knowledge graph analytics uses both symbolic and numerical learning to predict future trends. Symbolic learning finds patterns in the graph, while numerical learning helps in predicting links and understanding cause and effect. These capabilities address the need for context aware reasoning by drawing insights from medical knowledge and data. In lung cancer treatment, for example, these analytics support tasks such as assessing the risk of relapse and exploring treatment scenarios. Various techniques will also be used to generate benchmarks of synthetic knowledge graphs for the empirical studies of TrustKG tools. Human machine communication makes it easier for people to understand insights and trust the information they read. This layer ensures that clinicians can understand recommendations and make informed decisions. TrustKG makes it easier for clinicians to trust the AI results. Example of human machine communication is TrustKG uses Interpret Me, a system that shows the details of machine learning model so that clinicians and researchers can understand them better. TrustKG also uses OrKG Ask, a hybrid system that supports vector search, large language models, and knowledge graphs. This allows scholars to search and explore. In TrustKG, OrKG Ask provides advanced query and exploration capabilities, helping clinicians to understand AI-driven insights in a broader research landscape. TrustKG addresses two core prediction tasks critical in oncology: predict valid relationships and counterfactual prediction. These tasks are of great importance for the implementation of personalized treatment strategies and the anticipation of patient outcomes in complex scenarios. Predict valid relationships is a link prediction task that is about assessing the likelihood that a given link is accurate. In lung cancer, this can mean predicting the probability of relapse based on biomarkers and other factors. Accurate link prediction helps in identifying at risk patients and improve prognosis. Counterfactual prediction. Counterfactual reasoning is a way of thinking about what might have happened if something had been different. In lung cancer, these helps us to understand how changes in lifestyle like quitting smoking, might affect the disease. This is important for planning treatments and preventing the disease. This example shows how patient attributes and treatment protocols are linked. The model checks if the treatment is suitable for a patient with certain characteristics, example, age, gender, and genetic mutations. Shapes represent set of conditions that nodes or edges must satisfy to ensure data consistency and integrity in knowledge graphs. Inductive learning in knowledge graphs derives general patterns from specific data to make predictions about unseen facts. An ex- this is an example of how to use counterfactual reasoning to see how a changes in habits might affect patient biomarker, which helps to make personalized treatment decisions and plan preventive care. The model examines how changes in lifestyle factors such as smoking habits might influence a biomarker status related to lung cancer. For instance, it assesses if switching from a current smoker to non-smoker could affect the ALK mutation status. VISE is a comprehensive hybrid framework that encompasses the enrichment, validation, and transformation of deduced knowledge based on observed explicit patterns to infer meaningful predictions. Symbolic learning here means logical rules. A rule suggests that patient receiving nivolumab for stage 3A of lung cancer are more likely to exhibit certain biomarkers. Shakal constraints are used to validate predicted links. A constraint checks if the patient with an EGFR mutation should not be recommended the drug nivolumab. The rules and the constraints are used to change the initial knowledge graph into a more detailed one with both positive and negative edges. In learning of knowledge graph embedding, the model is trained on transformed knowledge graph. This captures both validated and negated relationships in the low dimensional representation. Finally, link prediction phase. The embeddings are used to reduce new plausible links. The pipeline shows how WISE combines symbolic rules, constraint validation, and numerical learning to enhance prediction accuracy in knowledge graph. We report the effectiveness of WISE focusing on knowledge graph embedding models TransC, TransD, TransH, and RotateE in the context of lung cancer relapse prediction problems. The table shows the comparison between the baselines and the WISE for link prediction. The analysis revealed a robust performance compared to baselines. Knowledge graph embedding models are trained over the LCKG, that is, positive edges, to predict missing links. The results show that we need to understand how the knowledge graph embedding model works. WISE improves knowledge graph embedding model performance and explains predictions. WISE knowledge graph embedding models perform slightly better than baselines. The negative edges generated by symbolic learning improves WISE performance. Adding heuristic-based negative edges to the knowledge graph, eh, WISE shows a drastic change and improvement in the performance. Experimental evaluation shows the traditional ML models and knowledge graph embeddings have complex patterns of performance and predictive capabilities. The table shows the classification outcomes of decision trees and random forest in three configurations. The table at the top shows the decision trees performed best for predicting relapse progression. The table at the bottom shows the random forest performance. Random forest also struggled with no relapse prediction, suggesting it has limits when there are many different types of data. The figure shows the overlapping analysis where rotate-T is the best of the inductive learning approach for decision trees. This suggests it can capture both traditional patterns and complex relationships. Transy and rotate-T showed a strong alignment in their predictions. Around 190 predictions were shared, indicating that rotate-T can preserve translational relationships while adding rotational modeling power. The lower overlap between Transy and Trans-D, that is around 142 prediction, shows that these models capture different relationships in the SLCKG. Here we present the problem of counterfactuals using healthcare AI. Healthcare AI solves the problem of counterfactual prediction by performing these three main tasks. First is symbolic reasoning, causal model learning, and counterfactual prediction. The figure illustrates the patient named Eva, a non smoking female lung cancer patient. Her biomarker result is positive. Under a hypothetical condition, we want to predict her biomarker result if she were a smoker. Healthcare AI utilizes symbolic reasoning to extract domain knowledge from a knowledge graph. This includes two parts: metadata stored within the knowledge graph and Horn rules mined from an enriched knowledge graph that incorporates facts inferred from the knowledge graph. During the causal model learning phase, a large language model uses domain knowledge to understand the relationship between the properties of the target class. A statistical model also learns causal relationships from the knowledge graph. The inferred relationships are added to a single causal graph G. This is done using the method specified in the causal model learning component. The causal model is then learned using data from the knowledge graph. Finally, this causal model is given the contextual properties of EVA and a hypothetical treatment. It then infers the counterfactual biomarker result of EVA if she were a smoker. We report the results of causal discovery task. Healthcare AI outperforms other methods in all synthetic knowledge graphs. Data-driven method, that is baseline 1, gets better as the data size gets bigger, but not as big as 5,000 or 10,000. It may not be possible to learn the causal graphs from data alone. Metadata or knowledge-driven methods like baseline 3 can infer some causal relationships that baseline 1 cannot. This is why healthcare AI performs best in all the synthetic knowledge graphs. We learn causal models from the data sets using maximum likelihood estimation method. The Pearson correlation coefficient metrics for the causal model by each method are presented as the mean standard deviation using five-fold cross-validation on all patients and their counterfactual. The causal model trained based on the expert causal graph has the lowest performance, possibly due to overfitting. This is probable because the expert causal graph is complex and needs large data set to learn the causal model's conditional probability tables. The simpler structure of causal graphs reduced by PC and FCI method allow for effective learning with small datasets. The results confirm that healthcare AI outperforms the other baselines and exhibits a good counterfactual predicting performance with baseline 4. These findings suggest that explicit representation of semantics within causal models contributes to better decision making and will facilitate human machine communication by making results more interpretable and contextually grounded. VISE and HealthCare AI uses knowledge graphs and symbolic reasoning to solve important problems like predicting links and counterfactuals. Semantic integration improves predictive accuracy and supports more accurate causal discovery. VISE achieved enhanced hits at 1 and MRR scores, while healthcare AI outperformed baselines on metrics like Jacquard index and F1 score. Additionally, healthcare AI's use of counterfactual reasoning achieves similar results to experts, showing how domain-specific knowledge can improve AI in healthcare. Our future directions include reducing cost. Our approach is effective but increase cost. Future work should focus on making these models more efficient. Principal versus neurosymbolic systems. We need to look at both principled and integrated way of doing neurosymbolic AI. Principled seems keep the symbolic and neural parts separate, while integrated systems combine them more. Research into the pros and cons of each approach can help to create hybrid AI systems that work best for patients, enhancing the usability through better visualization and user interfaces. As usability is a key issue in using AI in clinical settings, better visualization and user interfaces help users and clinicians. Also, understanding what users need will help us create tools that fit clinical workflows and support decision making. The future directions aim to make hybrid AI systems in healthcare more practical in real world applications. The integration of semantics within AI holds substantial promise, not only for advancing predictive accuracy but also fostering trustworthy and human centered AI in medicine. Thank you for your attention.